In the second part of section 6.3, we'll study optimization problems with inequality constraints. For simplicity, consider this minimization problem. Minimization of x squared. Now we choose f of x is x squared, subject to x is larger than or equal to 1. In this figure, the curve is y equal x squared. And we try to find the minimum when x is larger than or equal to 1. Apparently, this value is the minimum value. So here, by using f notation, the optimization value is 1 when x is 1. So we know the answer. Now we'll try to solve the problem using optimization theory. First, we rewrite the constraint in this form and formulate the Lagrangian. And f of x minus alpha times x minus 1. And we consider this minimax problem of the Lagrangian subject to now the Lagrange multiplier is non-negative. Then we have here a claim. The original minimization problem, that one, is equivalent to the minimax problem. We'll see first some detailed proof, and later we'll consider a formal proof. When x is strictly larger than 1, then this portion, that portion, and along with the extra term, because x is not being touched, so that we consider this portion, then maximum over alpha non-negative when x is strictly larger than 1. This portion is positive, that is non-negative, and with this negation, this is always negative. In fact, non-positive. So the maximum value must be 0 when alpha is 0. So it becomes, the Lagrangian becomes the original objective function. When x is 1, then this is 0. So for arbitrary choice of alpha, this value is always 0. So it is 0. So the Lagrangian becomes again the original objective function. Now, when x is less than 1, which is violating the constraint, then the maximum over alpha of that portion. Now, x is negative, so that this portion is less than 1. So this one is negative, and along with that, here, if alpha is non-negative, then maximum value will become infinity. And we can choose alpha very large, so it becomes infinity. However, in front of this maximum function, the operation, we have minimum operation over x. So that minimum will not make this happen. In fact, the minimization part is fighting maximization part. And so that when the x is violating the constraint, then the objective becomes very large, so that the minimization will push x increase, so that eventually x becomes larger than or equal to 1. That means that satisfies the constraint. So in other words, the minimization forces the maximization to behave, so constraint will be satisfied. So eventually, and this whole thing is equivalent to the original minimization problem. The proof is a little bit foggy, and now we'll go to formal argument for the equivalence. Now we start with f of x equal x squared, and f star is the optimal value of the original minimization problem. And we rewrite here minimization over x, f of x, subject to x is larger than or equal to 1. For this one, once x is larger than or equal to 1, then here the Lagrangian, and because alpha will be chosen to be non-negative, this portion is always non-positive, so that the Lagrangian is always bounded by f of x. Of course, its maximum happens when this portion is 0. So we have this result. How about x is violating the constraint, which means that x is now less than 1. Then here, earlier we checked that in this case, the maximum of the Lagrangian is infinity. So x can be either this one or, in fact, satisfying this one or that one. And for these two cases, we have this conclusion. Now, we try to minimize this term over x. Then this is infinity, that is f of x, so that we can get this one here. That must be f of x when x is larger than or equal to 1. That problem is exactly the same as the original problem. So its optimal value is f star. So we can reach that one, which means that the original problem and this minimax problem will have the same answer. So they are equivalent. And we have to notice this one. This minimization does not require x to satisfy the constraint. In fact, this minimization is over all possible values of x. And even though we do that, here from these two, we get this conclusion, so that once we write down this way, then the constraint is only alpha non-negative, and there is no constraint for x. However, this problem, minimax problem, is equivalent to the original problem. Okay, here the minimax problem is equivalent to the primal problem. So we write down here. So now the constraint is the Lagrange multiplier non-negative. So we can say this is the primal problem. And the Lagrangian is defined in this way. Here we'll define dual problem of that primal problem by swapping the minimization and maximization operations. Just simply we swap that to get the dual problem. This portion is called the Lagrange dual function, and now here alpha is also called the dual variable. the reason we consider the dual problem is here, for example, that optimizes F star, and this optimization optimal value is G star. Then in theory, we know that F star is always larger than or equal to G star. If they are different, then we have a little issue. However, in our simple problem, in fact, F star must be the same as G star. And in this case, we say that it's a strong duality. Once this inequality is strict, then we say it is a weak duality. But for convex, the optimization problem, it'll be strong duality. Now, rather than solving this problem, in most cases, solving this problem is much easier. So that we'll try to solve this problem, and then the optimal value will be used for that one. Okay, that's the strategy. The reason is basically in Lagrangian, once okay, for that one, it's a kind of linear with respect to alpha is combined, so that in fact this one is a kind of a lower hyperplane with respect to alpha, and so that once in general dimension, if we have objective function, then it's a kind of lower hyperplane is made along with this Lagrangian, and try to find the possible max-min optimization, so that that will be here now touching here. So eventually, once you try to maximize with respect to alpha, then certain hyperplane will be made, and then that will be the optimal value. And for this convex problem, always this is satisfied, so that no problem. The original problem is not easy to solve. This one is easier. So we'll try to do that. Okay. Now, first we try to solve this portion, minimization of the Lagrangian. Okay. Then we can do it by using the quite familiar calculus technique, just a derivative with respect to x. Then we can get 2x minus alpha. Now we set it 0. Then x is alpha over 2. By using this equation, we can express the Lagrangian as a function of alpha, replacing x by using alpha over 2 here. So we reach at that one. Now we try to maximize this Lagrangian over alpha. So the problem becomes here. This can be easily solved. And if you try to make a graph, then you can see in this way. Okay. Now, for that one, once alpha is 0, then it's 0. And once alpha is 4, okay, then it is 0. Okay, so that the graph of this function of alpha can be given in this way. That is 4, and at 2, it is maximum. Okay. So when alpha is 2, the maximum value is 1 now. You can easily see that. Or you can use derivative technique. From here, if you make a derivative, then 1 minus alpha over 2 equals 0. so that we can get alpha is 2. Okay, when alpha is 2, the value is 1. Okay. Now we found the optimal value alpha star, which is 2. Then you can plug here and you can decide x, so that now x is 1, and you can finalize the answer. Or now you can, because we already know alpha is 2, then from Lagrangian, now alpha is replaced by its optimal value. So we recheck that one. And then this can be reformulated in this way, which means that the Lagrangian is minimum when x equals 1, the minimum value is 1. That is the final answer. So by using various techniques, we can get the same result. But here the idea is, through this dual problem, maximum problem, we can get the solution much easier than solving original minimax problem. So that's the reason we try to use the dual formulation and try to get the solution more effectively. But once it is not strong duality, then we may have some issue, but that is over the class, so that we'll not deal with that here. Okay. Now, finally, in this section, we'll consider multiple constraints. Consider this problem. Now, maximization of f of x subject to these two equality constraints. Then we'll consider geometric interpretation when extremum happens. Then the gradient must be in the plane of the gradient of g and gradient of h, which means that the gradient of f must be a linear combination of the gradients of these two functions. So here we formulate these 5 equations when the function is defined over R3 in x, y, z. Now, gradient of f is the same as lambda gradient of g plus mu gradient of h. So gradient of f is a linear combination of gradient of g and gradient of h. And we have these two constraints. So there are 5 equations, 3 from here and extra 2 from constraints. And we have to decide values of x, y, z, and lambda mu. So 5 variables. We can solve this system reasonably, but it doesn't mean that we have a unique solution. It is not a linear system, so that you can have more than one solutions. See this example. Find the maximum value of function f of xyz equals c. We chose very simple objective function, and on the curve of the intersection of the cone and plane. Now that is, here we define from here g of xyz, and from the second constraint plane we have the function h. Then by using this formula, we have this one. Gradient of f is lambda times gradient of g plus mu times gradient of h. Now, line by line, term by term, we write in this way. So we have 3 equations and extra 2 equations. Now, from the hint is saying that from 1 and 2, we can conclude x equals y. In order to do that, we have to show that lambda is non-zero. Okay, for this portion, once lambda is 0, then this vector must be the same as mu times the vector of all ones. It's impossible, so that lambda cannot be 0. Once lambda is non-zero, then here this is same, and left-hand side is the same, so that here 4 lambda same, so that x must be y. And if we plug this one to over there, then we can reach at here that one. So that by using these two equations, you can express that one quite simple function of one variable, so that you can decide the one variable. Then here you can decide other two. So you can finish the computation yourself. Okay, that's the end of the section. Thank you.